In today's presentation, we will be discussing the Rayleigh Criterion. My name is Joey Tafuna'i from Brigham Young University, and this is for a Physics 106 class. Have you ever wondered late at night when you see a vehicle in the distance, for example in this image here, whether that light source is two headlights or one, for example, a car or a motorcycle? We'll come back to this image later, but hopefully by the end of this presentation, we'll be able to answer this for you. Before we discuss the Rayleigh Criterion, we must review a few concepts that are necessary to better understand it. The first concept we'll talk about is diffraction, and then we'll talk about resolution. And then following that, we will discuss the Rayleigh Criterion. For diffraction, we know that light travels as a wave. When we view it from above, it looks like this, and these peaks show up as these wave fronts. Here in this image, you see the wave fronts as they travel towards an opening and an obstacle. This definition, the bending of a wave around the edges of an opening or an obstacle, is called diffraction. So, as light traveling towards this opening hits it, it will be diffracted and curves, and then will go on. And for example, if the light hits a wall, it may produce a diffraction pattern as such. Here in the center, we have a high intensity, and then there are some interference patterns. Here we see a destructive interference pattern, a constructive interference pattern, destructive, constructive, and the light begins to dim. Another way to view this is here in this top image. The center has the highest intensity, then we have some sort of destructive interference, then some constructive, destructive, and then constructive. Keep this image in mind for when we talk about the car headlights again. Okay, now we'll talk about resolution. Resolution is the ability to discern that two light sources are actually two different points and not one. So, for example, in A, we have one light source, but in C, you might not be able to tell that it is. I mean, here it's kind of obvious, but for somebody standing at a distance, you might not be able to tell that they are separate points. Here in B, it is much more clear that they are in fact two different light sources. So resolution is our ability to tell that they are two different light sources. Okay, now that we know that diffraction, which is light traveling as a wave, can be bent through an opening and produce a diffraction pattern, and we know that resolution is our ability to discern that there are two light sources, we can now discuss the Rayleigh Criterion. Here, this equation, theta is equal to 1.22 times the wavelength divided by the diameter. This equation is what we can use to determine if the Rayleigh Criterion is met. That criterion is the minimum angle of theta where two images are just resolvable when the center of the diffraction pattern of one is directly over the first minimum of the diffraction pattern of the other. Okay, there's a lot to unload there. So let's go to this image to see if we can make that clear. So we have two images. As discussed in the definition, we want to know when they are just resolvable as they pass through this circular aperture. And so as they pass through, they are going to produce a certain, as the light travels, it's going to produce a certain angle between the two light sources. And then, as we talked about with diffraction, it'll pass through the circular aperture and be diffracted, and then produce a diffraction pattern on this opposite wall. Here we see the intensities measured of those light sources on that wall. And our definition says that this angle, the minimum angle required to meet the Rayleigh Criterion, is when the center of this diffraction pattern is right over the minimum, right here, the minimum of the other diffraction pattern. This is the maximum and the minimum of the right-hand diffraction pattern, and is right at the center. And then this other diffraction pattern's minimum is right over the center of the other. So in this case, this theta would be the minimum angle required to meet the Rayleigh criterion, which, if it is met, we are able to discern that these are two separate objects. We are able to resolve that. Okay, let's go into a little more explanation, essentially of the same thing, but hopefully to make it a little more clear. Here we have two light sources. Those light sources are fairly close together, and I'm just going to say that this will probably not be discernible, as two separate light sources. So we have a certain theta associated with these light sources as they pass through this circular aperture. As they pass through, we see that the minimum of this diffraction pattern is past the center of the other diffraction pattern. So in this case, the Rayleigh criterion is not met, and we would not be able to tell that these are two separate light sources. Now, if the light sources were a little further apart, that would produce a larger theta as it passes through the aperture with a specific diameter. And notice that the minimum of this diffraction pattern is right over the center of the other, and vice versa. So in this case, our theta will be theta minimum to meet the Rayleigh criterion. And then here in this instance, we are able to, so what have we changed in this situation? The theta's changed, but why has the theta changed? Because our light sources have not changed in distance from each other. So the reason theta has changed is because we have increased the diameter of our circular aperture. So as the light travels through, we see that our diffraction pattern's minimum is well within the center of the other diffraction pattern. In this case, our resolution has gone up, and we are even better able to discern that these are two separate light sources. And that would just show up as a greater theta. So notice this is the smallest theta, a larger theta, and an even greater theta. Okay, so now let's go back to our image. Notice how it's a little blurry in the light. That is going to be related, I'm going to go back to the other image, to this light image here. The reason it's blurry is because there are interference patterns, and that causes that blurriness. So, at this distance, we aren't able to tell that it is two separate light sources because we have not met the Rayleigh criterion. But as these sources come closer, our theta increases and our resolution increases, and we are able to tell that they are two separate light sources if it is a car. Okay, and this is just a diagram to show that. Here we have a certain theta, theta 1, associated with the light sources as they travel through a circular aperture. In this case, it's the pupil of our eye. Another way that you could increase this is by dilating your pupil, giving you better ability to resolve these two different images. Or, as the light source gets closer, the theta increases, and our ability to resolve the two separate images increases as well. Okay, so I hope that clears up the Rayleigh criterion. To finish up, we're going to go through an application question and see if this, just see how we can apply this to other types of circular apertures. So we've got a space telescope, and it has a circular aperture. And as we look into space, we want to know how well we can tell the difference between two different stars, for example. So I'll read the question. The primary mirror of an orbiting space telescope has a diameter of 2.5 meters. Being in orbit, this telescope avoids the degrading effects of atmospheric distortion on its resolution. What is the angle between two resolvable point light sources, perhaps two stars? Assume an average light wavelength of 550 nanometers. So here we have our telescope, our circular aperture that has a specific diameter, and our two light sources, our two stars. Okay, give this video, we'll pause this video and see if you can give this question a shot, and we'll discuss the answer in just a moment. Okay, so our equation for the Rayleigh criterion is theta is equal to 1.22 times the wavelength of the light divided by the diameter of the light. The diameter of the circular aperture. So here I've drawn up a diagram. As the light travels, it's going to pass through the circular aperture, and it has a specific diameter. That is going to produce a certain angle, theta, and our light source has a specific wavelength associated with that light. So theta is equal to 1.22 times the wavelength, and this is going to be in meters, so it's 550 times 10 to the negative 9th meters, or 550 nanometers, because that was given to us in the example. Okay, and that's divided by 2.5 meters, which is our diameter. Our diameter, as set up on the top, diameter of 2.5 meters. Okay, so we have our units correct. And as we multiply this out, 1.22 multiplied by 550 e to the negative 9th divided by 2.5 will equal 2.64 e to the negative 7th. And if we are able to discern that these are two light sources, then this theta has met the Rayleigh criterion. And if it's just resolvable, just barely able to tell that they're two separate light sources, that's when we have found theta minimum, and we have met the Rayleigh criterion. Okay, if you have any questions about the resources that I used for this video, here are my references for all the pictures and the information, and I hope this was helpful.